This is the Parvati. Parvati. This is the Parvati.
Okay, hello everyone. We'll wait for 2 more minutes in case more people are joining. In the meantime, I'll share my screen. Okay, maybe we can start 6-5. Okay, so welcome everyone for this problem solving session. So now we are at the halfway point of the course, so you know what this is about. We are slowly moving into, actually writing down the different Lagrangians that describe the various interactions that happen in the standard model and what kind of symmetry and what kind of groups they map onto and what kind of equations of motion they follow. So based on this, we are slowly constructing the standard model step by step, right? So yeah, as I said, this is like week 6 of these problem solving sessions. So my name is Zenia. The point of these sessions is that we solve some problems together, do a recap of the material over the week. And it's also to give you this forum to have this live interaction with someone, so that you can clear your doubts regarding the course and other things, right? So this is the idea behind these sessions. So as always, all these sessions are recorded and the slides are also available to you. I hope you have been able to access them. I also maintain a link on my website. Just give me a second also. Yeah, if you just go to the link, then this is like the website. You can find the YouTube playlist. Here you can see that the various videos have been uploaded, and also the slides of the sessions have been uploaded in this Google Drive over here. So this is, yeah, I've been uploading the slides. So once this class is over, I'll be uploading for this week as well. Right. So I hope you've been able to access these materials, even if you're not able to join in live. Although I encourage you guys to try to join live, it's good to have some participation. Anyway, you have your recorded lectures for the rest of the course. So to have some live interaction for at least once a week, 2 hours, you can really engage with the material. I think it really helps you in your course as well. Okay, so yeah, again, if you want to, I would highly recommend that you mail me if you have any specific agenda that you want me to discuss. So what I do is I usually just prepare some slides based on the week's topics. But if you have some particular agenda you want me to go to in depth, or you want me to cover in depth, then if you mail me, I will try to cover that in the class. And if you have any other doubts regarding the course material, also I'll be able to help you. I'll also just paste my website in the chat so that you can save that for later. Okay, anyway, so right, so fine. So that's about the course. So as I said, we are now at week 6 of this course. So we have now, we have now moved past the early days when we were talking about, the four fundamental interactions and, discrete symmetries. Now we are actually trying to cast them in terms of, mathematical objects. So last week we spoke about the Klein-Gordon equation and the Maxwell equation, as well as the Broca equation, which are applicable for spin 0 and spin 1 particles respectively. This week you saw a little more about the Dirac equation, and more importantly, you saw about a little more in depth about the Lorentz group. So the Lorentz group is very important because, as we have been continuously saying throughout this course, whatever theory we write down in the standard model Lagrangian or as part of the standard model and its interactions has to be Lorentz invariant, or it has to be a covariant theory. So remember, for example, when we wrote the electromagnetism field tensor, it is very important that we can't just write it in terms of E and B themselves, but we had to construct this sort of field tensor F mu nu and then write the Maxwell equations in that form, because then only we got this frame invariant quantity that we could use to then define, the equations of motion in terms of either that quantity or the vector potential, which is the actual 4 vector. And then from that, we could derive, the equation of motion, which is in this case, it is a Maxwell equation. Then by gauging that equation, we are able to get the different polarizations for the photon and so on. So my point is that whenever we write a theory in this regime in standard model physics, it has to be Lorentz invariant. So we have to understand what the Lorentz group entails. So remember, I've been saying that group theory is kind of like the grammar of the standard model. That is because uh, that's because group theory is really how we are going to be describing, first of all, what kind of objects the particles are. Are they spinors, are they vectors, are they scalars? That uh, directly tells us about the degrees of freedom, because spin is related to degrees of freedom, as you've seen by now. And then also, the symmetries and of the various groups and their behavior kind of tells us about what the interaction pattern is between the particles and the force carriers, for example, which are themselves particles, right? So remember, we are now in the regime of quantum field theory, where we have combined quantum mechanics and special relativity, and we are writing things in terms of mode expansions, and you can think of it in terms of bunch of harmonic oscillators. And we are trying to do this so that we yeah, because we want to write a relativistic theory of quantum mechanics. Okay, so we already saw the first attempt to do that. I think last 2 weeks ago we saw the Klein-Gordon equation, which was sort of the first attempt to look for a relativistic theory of quantum mechanics. We saw that the Klein-Gordon equation is not a generic equation. It has issues in terms of negative probabilities, etc., which could be interpreted in terms of antiparticles, but still, it's not applicable for every particle. It's only applicable for spin zero scalar fields, right? So the next person who tried to kind of give a theory or give a relativistic quantum mechanical equation was Dirac, and he gave his name to the Dirac equation, which actually describes spin half particles. So I wanted to just kind of yeah. So this is basically the various equations of motion, and obviously each of these is derived from a corresponding Lagrangian. You've seen how to write. We have to write a Lagrangian, then we have to kind of get the equation of motion from the Lagrangian by the same machinery we use in classical field theory, which is the Euler-Lagrange equations. The point is that in quantum field theory, once you get a solution, a wave solution, you then further try to quantize that wave solution in terms of these different modes that the particles can occupy, the different momentum states the particle can occupy, which makes it a quantized field theory or a quantum field theory. Okay, so today we'll be kind of looking at the Dirac equation. So I have some quick videos. I'll just show these. These are only like 2 or 3 minutes each. So I want to just motivate to you the Dirac equation, why it has the form it has, and more specifically, what's very interesting is that when we write the Dirac equation, you write I gamma mu d mu minus m psi is equal to 0. That is a Dirac equation. Here, psi, the wave function, is not a simple wave function or a complex quantity like we used to have in the Schrodinger equation or the Klein-Gordon equation, but it ends up being a vector, right? It ends up being a 4 cross 1 vector, and you find out that there are actually two particle solutions and two antiparticle solutions that come up in this context. So we can also see how that structure is imposed by just trying to write the Dirac equation. So I wanted to motivate that for you. So I'm just going to play the video. Okay, I hope it plays here. Let's see. Okay, it always has some error with the video player, but okay. Let me just play this video for you because it's a nice derivation of the Dirac equation.
How can we describe particles in quantum mechanics? The Schrodinger equation takes the Hamiltonian p squared over 2m. This is the classical energy-momentum relation. The Klein-Gordon equation has a relativistic energy-momentum relation where the energy is given by E squared equals P squared.
So remember, this is how we also derive the Klein-Gordon equation. We first wrote the energy E is equal to P squared C squared plus M squared C power 4 kind of thing. But here, of course, the reason why you don't see any C's is because we are working in natural units. As I mentioned, or as you have seen through the course, a lot of high energy physics is done in natural units. So you'll usually see that C, H cut, those things are just set to 1. So they might be missing in the formula. But just remember that, they are there. Otherwise, it's not, otherwise this is not dimensionally consistent. So there's a C square here and there's a C power 4 here, both of which have been set to 1.
Plus M squared. But in this equation, we have a second order time derivative, which is the cause for some problems regarding the probability density. This means for the Dirac equation, we want a relativistic energy momentum relation, and we want only a first order time derivative. A general Schrodinger type equation looks something like this. I dt acting on psi is a Hamiltonian acting on psi. And for this Hamiltonian, we make the following ansatz. We assume that there is momentum and mass with some coefficients alpha and beta acting on the wave function psi. This means we have to...
So basically, instead of starting with the energy momentum relation like we did in the previous two cases, here what we are trying to do is we are trying to just put some linear combination of momentum and mass. And yeah, we wanted to ultimately give us a single a power of the time, because higher order power of the time is what caused those negative probability density and other things in the previous case. So we don't want a sort of D'Alembert kind of form that we saw in the Klein-Gordon equation. We want to stick to the original Schrodinger equation where we have dt psi and then id d by dt psi is equal to h psi. But we want to also capture. So instead of trying to impose h is equal to something, we are trying to keep d by dt psi on one side, and this expand in some coefficients, and then by matching the coefficients you can find out what exactly is the Dirac equation. So this is the idea.
Find out the coefficients alpha 1, alpha 2, alpha 3, and beta. Our condition that this is a relativistic energy-momentum relation is that if we apply the Hamiltonian twice, it should yield p squared plus m squared. Or in terms of indices, pi plus m squared.
So this is just energy square is equal to p squared plus m squared. But to find the form of h operator itself, you're just going to equate that with this. So if you just square this, that's what the person he is writing here right now.
Let's find out what this condition implies. We have alpha k pk plus beta m times alpha j pj plus beta m. And this should be pi plus m squared. Notice two things. First, we left out the sum sign in these terms, following Einstein's summation convention.
Yeah, so whenever two indices are repeated, they are summed over. That's Einstein's summation convention. So when you write alpha k pk, that actually means alpha 1 p1 plus alpha 2 p2 plus alpha 3 p3. I think you guys know this, but yeah, instead of writing this sigma, you can just write it in terms of this.
And secondly, we chose a different index in the second term, j instead of k, to avoid any ambiguity. If we multiply these terms and keep their relative orderings, we end up with something like this. Let's first look at the terms without any momentum. This means beta m on the left and m squared on the right. Beta squared should be equal to 1, and we have our first condition. Next, we look at terms with only one momentum. This means these two terms on the left and nothing on the right. So we have alpha k pk.
So right now what's being done is a very simple, just equating the coefficients on the right hand side and the left hand side. Right hand side comes from, relativity p square c square plus m square c power 4. On the other side is our ansatz, which is that h is linear in p square and m, and that's what's being done here. So we're trying to narrow down put some conditions on alpha and beta so we can determine them.
Beta m plus beta m alpha j pj has to vanish. If you rename some indices, changing j into k, we can pull out a pk to the right, and we arrive at this condition here. This means that the anti-commutator of alpha k with beta has to vanish. Now onto the terms with two momenta. We have alpha k pk, alpha j pj on the left, and pi on the right. Here we can do a trick. We write this term again, but rename some indices, making k to j.
So this kind of index renaming and all these things are very common in tensor calculus. If you are not so familiar, just you can try working it out yourself. It just comes from the summation convention. And yeah, if you've done any GR or something, for example, this is very common. So yeah, if it's new to you, it might be a little confusing, but just basically these are dummy indices because we're summing them over. So we can always change their name to something else, and that allows us to do some nice manipulation. It's similar to how the integration variable that you have when you do an integration is always integrated outright. So in principle, you can name it whatever you want. So that can help you in some cases, right? That same kind of philosophy applies here.
J to k. So this term is exactly the same as before. If we add them and put a 1/2 in front of them, nothing has changed. Now we can pull out a pk pj to the right, and we're left with an anti-commutator again, meaning that the anti-commutator of alpha k, alpha j has to be 2 times the Kronecker delta kj. Now we finally have our third condition. It's worth noticing that the condition that an anti-commutator has to vanish is kind of strange, because usually it doesn't matter if we write x and y or y times x. Normally it just gives 2xy. And if this has to vanish, either the one or the other variable inside the anti-commutator has to vanish. But if we remember our ansatz for the Hamiltonian, this means that either the momentum or the mass drops out, and that can't be. So the smart thing that Dirac noticed was that if alpha and beta are not numbers but matrices, we can fulfill this condition without alpha and beta being 0.
So yeah, so this is Dirac's insight, right? Dirac got these conditions and it looked like it was implying that alpha or beta or both have to be 0. But that's only if we assume that alpha and beta are numbers. What Dirac realized was that if alpha and beta are matrices, then you can always you can, even the product of two matrices can be zero, even if each of the individual matrices aren't zero themselves, right? So that's what Dirac realized, is that these are not numbers, but they have to be matrices. So this theory, uh, by construction, when we try to construct and then we try to impose relativity in this way, we are automatically left behind with a higher dimensional case. Higher dimensional, I mean that we don't just deal with numbers, we are dealing with matrices. And that's why the, psi, as I mentioned before, it becomes a column vector, where two of the entries correspond to, a particle solution and the other to correspond to an antiparticle solution.
And if alpha and beta are matrices, then the thing they're acting on, the wave function psi, also has to be a column vector instead of a scalar function. That's pretty much it.
So
Thanks.
that's
And see you next time.
So that's about the Dirac equation. So I just wanted to motivate, probably it was covered in the class, but I just wanted to motivate you why exactly the Dirac equation, gave such a different insight when compared to the Klein-Gordon equation, right? When we looked at the Klein-Gordon equation, we just started the E square equal to T square plus M squared, and we did the same thing. Whereas if we don't impose what should be E first itself, and we try to expand it, and then we impose H squared to be equal to E squared, then we get this unique solution, which seems to imply that, there should be these a four column object that is representing the uh, the state of the particle. And today we know that this belongs to, the class of, SU2 symmetries. These are spinor particles that obey Dirac equation, and they have spin half. And we also know that Dirac equation actually is, a more generalized version of Weil's equation, where there are, two copies of the same equation within the Dirac equation, and the mass is kind of coupling them, right? We have left-handed spinor and a right-handed spinor, and the, antiparticle correspond, left-handed spinor and right-handed spinor. Yeah, there are basically two spinor equations within the Dirac equation. Mass kind of couples between them. So this also you have seen in your lectures. I'll touch upon it quickly, but yeah, this was a very interesting insight that Dirac had, and this is why he won the Nobel Prize in he is the second youngest person to have won the Nobel Prize. I think he won it at 31 or 32. So it was a very, very important way, because this actually represented again, a step forward to relativistic quantum mechanics. So I have another video. Let me see. Maybe we can just watch this also. This is about the Lagrangian itself. It's a short video again, just 2 minutes. So I'll just show you.
In order to construct a new theory, we usually start with the Lagrangian, or the Lagrangian density of the system. The reason for this is that if our system has some symmetries, then the Lagrangian will also respect these symmetries. In this video, we'll show you a very simple Lagrangian, the one of the Dirac equation. It looks like this. Let's investigate every part in detail. First, the most important part, the Dirac spinor. This is the wave function of a spin 1/2 particle. It has 4 components that can be interpreted in many different ways. One intuitive picture is to describe them as the spin up and spin down states of a particle and the spin up and spin down states of its antiparticle. Like the wave function in the Schrödinger equation, this is the object we want to calculate. But the spinor psi doesn't come alone. On the left, we have another term that looks quite similar. This is actually the complex conjugate of the spinor. More precisely, this is called the Dirac adjoint. It is composed of the Hermitian conjugate of the spinor and a gamma zero matrix. The Hermitian conjugate.
So the gamma matrices are the set of matrices that come in the Dirac equation. You can calculate them based on what I showed you before. So here, remember that in order to make the theory Lorentz covariant, so that it obeys Lorentz invariance, we can't just write the complex conjugate alone. You have to in the Dirac Lagrangian, you'll see that the complex conjugate always comes with this gamma zero matrix. I'm not going into detail of the gamma matrices. I think it's been covered in the class. If not, this channel which I'm using right now, it has a lot of short videos which explain these concepts. You can watch it, or in any sort of advanced quantum mechanics textbook, you will find about the gamma matrices. But basically, they have copies of the Pauli matrices. They are 4 by 4 matrices with copies of the Pauli matrices within them, and they obey something called Clifford algebra. So there are many representations of the gamma matrices also. We'll talk about these things a little more in the class, but yeah.
Means that this is now complex conjugated and transposed, therefore a row spinner. Don't call it a vector, even though it looks similar to a 4-vector. The gamma 0 is needed to build Lorentz invariant terms. The lowercase m is the mass of the particle.
So again, if you just have psi bar and you try to put psi bar psi, if you apply a Lorentz transformation onto it, you will see that it does not obey, I mean, it's not Lorentz invariant basically. So if you want to build Lorentz invariant terms that transform a scalar or vector or whatever, then you need to have gamma 0. That's just how the algebra of this system works. Similar to how in Minkowski spacetime, we have to have space and time mixed together, like that the algebra of this system is based on this kind of concept.
So if the spinner's size stands for an electron, then m is the mass of an electron. Finally, ID slash. The slash notation was introduced by Richard Feynman and is a convenient way to abbreviate a term like gamma mu something mu. I times a derivative is simply the quantum mechanical way of expressing the momentum of a particle in position space, and the gamma matrices make sure that the energy of the particle follows the relativistic energy-momentum relation, as we showed in the previous video. And that's pretty much it for the Dirac-Lagrangian. Thanks for watching.
So this is just the explanation of the Dirac-Lagrangian. I thought this will also be useful for you guys. And finally, one more way of how to get the Dirac equations from the Dirac-Lagrangian. Although, I'm sure you all know this. This is just, we are just going to see how applying the Euler-Lagrange equation on the, applying the Euler-Lagrange equation on the Dirac-Lagrangian will give us the Dirac equation. So we already saw what the Dirac equation should be like based on, this A, B kind of formalism, but here from the Lagrangian, how it looks.
Lagrangian describes a spin 1/2 particle using a 4-component spinner. In this video, we show you how to go from here to the Dirac equation. In general, to know how a particle moves, you need its equation of motion, or EOM in short. By knowing the Lagrangian of a theory, we're only one step away because the equations of motion for a given Lagrangian are simply its Euler-Lagrange equations. The Euler-Lagrange equations say that the derivative of the Lagrangian with respect to a certain field equals the derivative of the Lagrangian with respect to the derivative of the field. That was tough to say, but it should be pretty clear from the equation. Now, how do we apply this to the Dirac-Lagrangian? First off, which psi do we choose, psi or psi bar? The correct answer is both of them, but separately. Since the spinner has complex entries, we should actually do one Euler-Lagrange equation for the real part and one for the imaginary part. However, this turns out to be quite tedious. So instead, we can do a trick. We usually describe a complex number via its real and imaginary part. It's perfectly valid, however, to describe it using the number and its complex conjugate instead. If you know the number itself and its complex conjugate, you can easily calculate the real and imaginary parts. Okay, let's do this. First, we'll calculate the Euler-Lagrange equation for psi bar. The derivative of the Lagrangian with respect to psi bar is ID slash minus m psi. And the derivative with respect to the derivative of psi bar is 0. Let's just note d psi bar anywhere in the Lagrangian. There we have it. This is the equation of motion for psi. These equations describe how psi behaves and moves. Note that we calculated the Euler-Lagrange equations for psi bar, but ended up with the EOM for psi. Next, we calculate the Euler-Lagrange equations for psi. We could expect that this leads to the EOM for psi bar. In order to calculate the derivatives, let's rewrite the Lagrangian by multiplying the terms in brackets. The derivative of the Lagrangian with respect to psi is minus psi bar m. And the derivative with respect to the derivative of psi is psi bar I gamma mu. The Euler-Lagrange equations tell us that we need to differentiate this term once more. So this yields d mu psi bar I gamma mu. If we want to use a fancy notation, we could write this as psi bar d mu I gamma mu, where the arrow on top of the derivative means that we let it act to the left. This can be neatly expressed as psi bar I d slash. And altogether, this leads to psi bar I d slash plus m is equal to 0. To conclude this video, let's...
So basically we get back the Dirac equation from the Dirac-Lagrangian. So this is just to show that this is the Dirac-Lagrangian and this is how the Dirac equation comes about. I think the rest of the video is just them showing that if you take the complex conjugate of the psi equation, you get back the psi bar equation and so on. You can go ahead and look at it if you're interested. So yeah, I know these are equations and Lagrangians. I know there's a lot, but I would highly recommend that you guys try to sit and work out these equations at least once on your own. Then only it kind of sticks in your mind about what these equations are. We are not so used to them like we are with the Schrodinger equation, so it takes some practice to get us to that level. So I recommend that. Okay. So, right. So now let's just talk about the thing that I mentioned before, which is that we can interpret the psi column vector being 4 by 1 in a couple of ways. One is, of course, that the first two entries are particles and the other two entries are antiparticles, or like holes, as Dirac called them, negative energy states. Of course, we understand today that there's no such thing as an actual negative energy state. It's just an antiparticle, right? So let's see how the other way to interpret this is that there's like two copies of spinors in it, where there's actually a left-handed and a right-handed spinner in the column vector, and then that is what is actually being. So there's actually two Weyl equations that are there and this is called the Weyl representation of the Dirac equation. So let's see. So this is basically what happens when you expand. So this is a spatial part. So it's basically I gamma psi. Yeah, I del cross, which has gamma also, minus m psi is equal to 0. Where if we just keep I delta 0 or I minus I delta in terms of the momentum, like the 4 momentum, then you can write it in this form, right? This is a temporal part and this is a spatial part. So now what we are going to do is the 4-component wave function we are going to write as this way, where psi L and psi R are themselves 2-component column matrices, and this is the left-handed spinner and this is the right-handed spinner. Okay, and you can see that we can now write this in terms of this kind of Dirac equation. Okay, so here just keep in mind that this is still a 4 by 1 4 by 4 cross 4 matrix equation. This is still a 4 cross 4 matrix, just that this itself has two entries, this itself has two entries, and so on. So this itself is a block diagonal matrix. Okay. So this you can then, if you expand among, just based on the, if you just expand this based on matrix multiplication, you can see that this goes down to two equations, right? So you have P naught minus sigma dot P psi R is equal to M psi L. P naught plus sigma dot P psi L is equal to M psi R. So if we now simplify things further by considering a special case of a massless particle. So yeah, remember that the Dirac equation is for spin half particles. So can any of you give me the example of a massless spin half particle? Any examples for a massless spin half particle? Okay, so I'll tell you the example for a massless spin half particle or something very close to it is a neutrino, right? Neutrinos are not exactly massless, they have a very small mass, but within the standard model, they are considered to be massless actually. You will see that when you actually go through electroweak force and electroweak symmetry breaking, that neutrino is considered to be massless in the standard model. But again, from neutrino oscillations and other things, we know that neutrinos have a very small mass. We still don't know what that mass is. The experiments are still not there. But again, in the idealized world of the standard model, neutrinos are massless spin half particles. So whatever I'm describing right now is applicable for neutrinos. Okay. Fine. So we are going to first consider the special case of a particle which is massless. So m is equal to 0. So you can see that the right hand side just drops out, right? So you can see that now these are two independent equations. They are not coupled. In the previous case, they were coupled in the sense that if I want to solve this equation, I necessarily need to solve this equation and vice versa. I can't solve this independent of that because here psi L is there, and to understand psi L, I have to solve this. So I have to solve them together. Whereas here you can see that since these are independent equations, I can solve this and then I can solve this completely separately. So basically, the four component eigenstate psi L psi R. Remember, psi L has two components, psi R has two components, splits into two components pieces, psi L and psi R, that don't get mixed up by the equations of motion. It's as if the Dirac equation is telling us that we have two sorts of massless Dirac particles in nature: left-handed particles which have psi L and right-handed particles described by psi R. In the chiral representation, which is this, the Weyl representation or the chiral representation, left-handed functions live in the upper two slots and right-handed live in the lower two slots. So this is just the convention that people follow. But basically what this tells us is the mass is what, there are basically two species that are within the Dirac equation, which is the left-handed and the right-handed spinors respectively. And it's the mass of the species which causes these two things to get mixed up together, as you can see from the difference between 36.14 and 36.15. Okay. So this brings us to a nice description of the helicity. So remember that we described helicity way back in the first lecture or so, where we were talking about how helicity is basically whether or not the spin and the momentum are aligned or anti-aligned, right? So if the spin and the momentum are, or the intrinsic spin of the particle and the momentum are in the same direction, it has positive helicity, and so on. So you can see that we conclude that since psi L and psi R are eigenstates of the massless Dirac equation, then a free and massless left-handed particle will never change into a right-handed particle, right? Because these are eigenstates. So that means that if something is in psi R, it will continue to be in psi R if it's massless, right? Whereas massive particle, it has some information of psi L. Moreover, using the fact that for massless particles, eigenvalue of P0 is EPP. Again, this is just, if you think of photon, for example, the energy of a photon is PC, right? Because m squared c power 4 term drops out, so E is just PC. Again, here C is not there because we are in natural units. So don't get confused about C. By the way, all this is from QFT for the gifted amateur, I think chapter 36. So you can go see there's a chapter on the Dirac equation that you can check out. Anyway, so the this equation you can rewrite in this form, right? This means that massless states psi R and psi L are also eigenstates of the helicity operator with this. So from this discussion, it looks like chirality and helicity, while being represented by different operators, tell us the same thing. Okay, but remember that when we say chirality and helicity are the same thing, like left-handed means fixed helicity or so on, that is only true when we have this assumption, right? Which is that the mass is zero. So for a massless particle, the helicity is always fixed. It can either go with the particle or against the particle. And for example, in a neutrino, you only have left-handed neutrinos. So its chirality and helicity are the same. In the standard model where it doesn't have mass, you only have one kind of neutrino with a fixed helicity. However, helicity and chirality are identical for massless particles, but are in general not the same. Clearly, helicity tells us whether the particle's spin and momentum are parallel or anti-parallel. Helicity therefore depends on the frame in which it is measured. In the case of massive particles, it is possible to describe a particle with positive helicity, then to boost to a frame where the particle's momentum is reversed but spin is unchanged, thereby revising its helicity. So this is the important part, right? Because helicity is about the alignment of spin and momentum. Momentum can change between frame, but spin does not change. Spin is intrinsic property of the particle. If I take an electron and I put it in another frame, it's not going to suddenly become spin 3/2. It's always going to be spin half. Whereas momentum direction can always change between frames when we do, you know this from Lorentz transformations. So that's why For a massive particle, you can always do a frame transformation and change its helicity, right? Similar to how electromagnetic field can show up in a different frame when it's not there in one frame. However, for a massless particle, as you imagine, massless particles always travel at the speed of light as imposed by special relativity. So whether or not, and since the speed of light is constant in all frames, the massless particle is always moving in the same way in all frames, in which case, or we cannot change it to have, we cannot boost to a frame, where the momentum is going to be different. So that's why the helicity of a massless particle is the same as its chirality. It is an intrinsic property. Okay. So if we now consider massive particles, then the equations of motion revert back to 36.14. This shows us that massive Dirac particles involve both left and right-handed wave function coupled by the particle's mass. So this is what I was saying. We can think of massive Dirac particles oscillating back and forth in time between left and right-handed at a rate determined by their mass. This is most easily seen by looking at massive Dirac particles at rest, where we have this kind of expression. So yeah, so the main takeaway from all this is that the Dirac equation, even though it's a 4-component equation, you can actually think of it as two-component equations where there are, while spinners that are making up the Dirac equation. So you can see that, the reason we ended up with a 4x1 kind of thing was because we derived the Dirac equation. When Dirac derived the equation, he assumed it's a massive particle. And when mass is involved, it kind of couples both the parts of the equation. But this is just a special case. In general, it's just two parts of an equation. They may be coupled, they can be not coupled also in the massless case. So that just comes from the fact that Dirac started with a massive particle, that we get this form. If, for example, we had started with a massless particle, then we would have started with the Weil equation, and then later, if we added mass, we would have derived the Dirac equation from the Weil equation. So this is all just a matter of convention, right? So this is, I think, what is mentioned in the lecture notes also. This 4x1 is more of a artificial construct, whereas 2x1 is, the Weil spinners. So here, this is how it's written. Here, the psi A and psi B are kind of the psi L and psi R, which I used. So you can see that, yeah, psi A is psi L. If in particular representation, if you go, it is psi L. So this is kind of for spin half particles, if we consider it's this. And if m tends to 0, then, you just have independent equations. So once again, I just want to mention that if you want to look through this more resources for this, all the Dirac equation stuff, I linked those videos in the beginning because I think they're very nicely short videos that show how the Dirac equation is derived and other things. Apart from that, I think QFT for the gifted amateur, as I mentioned, it's not a standard QFT textbook, but it does cover a lot of topics in, more than just a popular level, with enough mathematics but not going too detailed. So it's very good for this kind of course where you need enough QFT to understand the standard model and you're not really doing a full semester of QFT. I think this is a good book for this context. Apart from that, we'll discuss a bit about groups. I think Alex Flournoy has a course of particle physics on his YouTube channel, but particularly his videos on groups were very useful for me when I took particle physics and standard model when I took a standard model class in my PhD coursework. David Tong's QFT notes are good, but again, that's more of a QFT resource. Apart from that, this book, Symmetry and the Standard Model, as you'll see, I've borrowed a lot from this book today. Chapter 3 of this book is all about group theory, and it goes into it in a lot of detail with all the mathematics, which is very nice, and I would recommend you look at it. This is also a mathematics textbook, although I haven't used it much. I've seen people recommend it. I looked at it a bit through this to prepare for these lectures, and I found it somewhat useful. And then this week, while I was preparing the lectures, I also found this website. So this is a website where there's a whole textbook on, or lecture notes on, group theory in physics. So again, there's Lie groups and other things. This is a bit more mathematical. It's definitely a little more mathematical than what I am comfortable with. So I didn't really use this much, but you can look at it in your own form. If you want to get proper mathematical theorems and other things, I would recommend this as a resource as well. So with that, before we do the questions, let's just look at a little bit of group theory, because as I mentioned this week, you looked at Lorentz groups, and it's very important to understand the symmetries of Lorentz group and how it leads to the different symmetries of the standard model. Because, as you saw, like the building blocks behind the standard model is based on symmetry and Noether's theorem. And the way that we encode this mathematically is in the form of continuous groups or Lie groups, okay? So remember that a representation of a group. So when I say a group, this is an abstract concept, right? A group does not always mean a fixed set of matrices or something. The same group can be represented in different ways. So a representation of a group is a mapping of the elements of G onto a set of linear operators with some properties, which is that it has some particular identity element, and the group multiplication law is mapped onto the natural multiplication in the linear space on which the linear operators act. So this is a mathematical definition, but what this means is, like, for example, rotations in 3D space, we can map onto the surface of a sphere, or we can write onto terms of matrices, right? So there are different ways in which we can encode the same information mathematically. So when it becomes a matrix operation, then combining two rotations becomes matrix multiplication. That's what this means. So this is a example that I saw on Wikipedia, which is quite nice, which is that, for example, if you consider the complex number, which is one of like some phase, basically, it has a property u cube is equal to 1. Then the set u1 comma u square forms a cyclic group under multiplication. So cyclic just means 1 into u gives u into u square, and so on. So basically u into u square gives 1, I think. So like that, it just forms a cyclic group because two of them give the other. So this group has a representation. So this is just in the complex plane, right? But if I want to get a representation in the complex square plane, like we talk about r square, r cube, right? Like that, if I take c square plane, then it gets mapped onto these three matrices. So again, these metrics are the same as that group. It's just that now we are in c squared, so they are 2 by 2 matrices. So similarly, if I look for c square, there's another representation in this form as well. You can also represent it in r square without going into the complex plane. If you just go to the rational plane, then you can see that this is the case with a and b having the real and imaginary part. You can even represent it in an r cube. So the point is that the same group is represented in different ways under different vector spaces, right? Depending on whether you're in r square or r cube or whatever. And this is what is going to be important when we talk about group theory, is that a group is not a fixed object. Like, a group is not a single object. A group is an idea which then can be applied to whatever vector space or whatever vector space you're working in. So that's the idea of representation theory. So you have to kind of think of a group as an abstract concept, right? And all of these have very precise mathematical definitions. Again, I'm not a mathematician, so it's possible that I'm using some of these terms wrong. I would recommend that you can go to that resource I showed you, which has a lot of very nice mathematical definitions. So Lie groups are groups. So we already talked about groups. Now we're going to talk about Lie groups. Lie groups are named after a physicist, Sophus Lie, and they are basically continuous groups. So for example, when we spoke about charge conjugation or parity or time reversal symmetry, those are discrete symmetries, right? Where we went from one point in space to another point in space, x to minus x. Whereas you can also have continuous symmetries where, you're not just going from two discrete points, you're actually doing a continuous transformation. So that is represented by a continuous group. So you can see that suppose the group elements depend smoothly on a set of continuous parameters, G of alpha, then this is what is called a Lie group. So this is the mathematical definition. So you can see that, it's based on the mapping, and there's some, it's a real smooth manifold. There is also a group, blah, blah, blah. So there's some, some more mathematical way of defining it based on what it maps to what it maps to. But for our purposes, as physicists, a Lie group is a continuous group. I think that's the best way that I've understood it. Yeah, that's what's worked for me. So these are some examples of Lie group. You can look at it. So for example, the set this is basically the real number plane under real number plane under multiplication. This is a continuous group. or a Lie group, and then the circle group, which is just the surface of a circle or the line which parameterizes a circle based on theta. That is also a one-dimensional Lie group. Okay, so the important thing about Lie groups and the very cool thing is that for the Lie group, you can define generators in a particular way. Okay, so generators are basically, as the name suggests, generators are objects which generate the whole group. Okay, so they are kind of like, instead of describing the group in terms of the group elements, which as you saw, the group elements itself may be different depending on what representation you're in. Instead of doing that, we can define a group in terms of the generators. Okay, so you can see that since identity is an important element of the group, it's useful to parameterize the elements close to the identity element in such a way that alpha is equal to 0 corresponds to identity element. So we are assuming that the group is depending on this smooth continuous parameter alpha. Then we assume that in some neighborhood of the identity, for the group elements can be described as a function of n real parameters alpha a, for a is equal to 1 to n, such that this, then if we find a representation of the group, the delinear operators will be parameterized in the same way. Then in some neighborhood of the identity element. So basically what we're trying to do is, because the group parameters depend on one parameter in a continuous way, we are trying to expand a group, one of the representations of the group, let's say d of alpha. G of alpha is mapped into some particular representation d of alpha. And what you're saying is that for small changes in the parameter alpha, you can actually Taylor expand this. And when you Taylor expand, you're left behind with these, Taylor expansion 1 plus df by dx, d square f by dx squared, and so on. So those terms, right, where we have called the parameter d alpha to remind you it is infinitesimal, and then the sum over repeated indices and so on. And x alpha is basically this. Okay, so these x alpha is actually the generators of the group. And you can see why, because instead of going like this, if I give you x alpha, just by doing this summation kind of thing, you can construct the group, right? So all the parameters are actually, if the parameters are independent, then x alpha xa is independent and I is included, so that if the representation is unitary, xa will be Hermitian operator. So that's some mathematics. The main point is now that instead of okay, I should not say representing, instead of denoting groups by their elements, which can be different depending on the representation, we can now denote the group by their generators. And again, the generators will also change based on what representation you're working in. Okay, so like generators in a particular representation does not have to be the generators in another representation. That's an important note to make. So this is the idea of generator, and you'll see why this is important when we talk about particle physics, why I'm spending so much time on this. So yeah, so this is all from, these were some mixed things, but after this I'm using from symmetry and standard model. Again, chapter 3 of this book goes into group theory in some detail, and this is a very clear description of group theory as I've seen in any textbook. Okay, so in general, there will be several, in fact, infinite different xis that define a given group. And this is just similar to how there are infinite number of representations of any finite group. What we will find is that up to a similarity transformation, a particular set of generators defines a particular representation of a group. So to define a group, you always have you can always choose some generators for some particular representation. So any element of a group in a particular representation can be written in this form. So this is just exponential basically. Because of the i's and other things, it just comes out to be the exponential of that. So the exponential of the generator basically reproduces the whole group for you. And remember, the generator, it's not a number. Okay, remember that it doesn't have to be a number, because as you saw, the representation of the group can be living in higher dimensional spaces, r square, r cube, c square, c square, etc. So for any group, the entire representation is defined completely by the generators xi. So again, the main idea here is to define a group. I don't have to call upon the group elements. I can actually talk about the generators instead, and that's an equivalent way of describing the group. Okay, so now let's move. So the other thing is the main interesting thing that leads to basically relevance for physics is that, okay, so now this is what is very interesting, and this is what will play a role when we talk about group theory in particle physics. It is clear that the commutator, that is xi xj minus xj xi, must be proportional to some linear combination of the generators of the group because of closure. We know that, all the elements of the group must, whatever combination of the elements of the group you do under the group element, it should bring back to something that contained within the group, that's closure. So because of that, we know that xi xj is something time xk, right? Some other element in the some other generator. So for some set of constants Fijk, these constants are called the structure constants of the group. And if they are completely known, the commutation relations between all the generators are known, and so the entire group can be determined in any representation you want. Okay, so now we have a third thing that we need to know, that we can use to reconstruct the group. So first of all, based on the group elements itself, you can reconstruct the group. The other thing is using the generators, you can reconstruct the group. The third thing is, if we know the structure constants, then we can just construct matrices that obey those structure constants, and from that we can generate the group. This is similar to how we construct the Dirac equation, right? When you're trying to construct the Dirac equation, what did we see? We saw that we got some anti-commutator relation and some commutator relation, like I showed you in the video. And from that, we defined an algebra, the Clifford algebra, and then we realized that gamma matrices are the mathematical objects which actually satisfy that Clifford algebra. Similarly, here also we have to see if we have to define some generators using we can define the generators using a particular structure constant, which basically define the commutation relations between the different generators. And these generators under the specific commutation relations defined by the structure constants form the Lie algebra of the group, and it is this commutation structure which forms the structure of the Lie group. So this is what is called Lie algebra. Okay. Okay, so now I'll just go through some quick examples to really cement this before we talk about the Lorentz group. But basically, you can see that we start by looking at a very simple group, SO2. This is basically orthogonal matrices of 2, and then S is for special, which means they are also unitary. This is the group of rotations in the plane that leaves R square is equal to X squared plus Y squared invariant. So this is basically two-dimensional rotations. So for some generator X, which we will now find of SO2, we know that V should be mapped onto this, say r theta, which is the element of the group, will be mapped onto this exponential, right? This is how generators are defined. Any element of the group is defined by the exponential of the generators. So we have just written that here. Any element of that group is defined by the exponential, and similarly you can write it for the VP also. So you can see that taking a combination of these two things, you can see that V goes to this, VT goes to this, and then if we combine them, we know that the group definition is based on this term being invariant. So if you just combine this, you can see that this has to go to 0 so that this term remains invariant. Under the group action. So from that, we know that x plus xt is equal to 0, which is that x is equal to minus xt. So x must be antisymmetric. Therefore, you can get x to be something like this. The I is to balance the I we inserted to ensure that X is Hermitian. So if you want to find any arbitrary element of SO2, you have to just take the exponential of this. So remember, this is the generator, right? The generator has to be put in an exponential, then only we get the elements of the group. So this is just a matrix. You're just expanding doing a series expansion for the exponential, and you can see that eventually it comes out to be cos theta, sine theta, minus sine theta, and cos theta. This is exactly the rotation matrix for a two-dimensional plane, right? This is what we know. So using the generator approach, because we know that rotations do not change the magnitude of the vector, they keep the magnitude invariant. Using that fact, you are able to define the generators. From the generators, you are able to generate the group. That's the whole point, right? Just by putting the generator in the exponential position, you are able to find out what is the elements of the group. Note that because SO2 is abelian, which is that for abelian groups are ones where commutation is respected, like in a rotation. Basically, if you rotate by in some particular angle and in a plane, and then you rotate by a second angle, it's the same if you do the second angle first and then the first angle, right? If I first rotate by 30 degree, then 40 degree, it's the same as if I rotate by 40 degree, then 30 degree. So this is a commutative group. So that's why the structure constants all vanish. So abelian group theories have zero structure constant. Okay, and non-abelian theories, in contrast, have non-vanishing structure constants. This is very important, and this will play a role in describing how different theories are different, why electromagnetism is different from the strong force, for example. So now this is an explicit example of a generator, and seeing how generator relates to group elements, we can move to slightly more complicated examples. So SO3 is 3D rotation. So obviously to describe rotation in a 2D plane, you only need one angle. But if you want to describe rotations in a three-dimensional plane, you know that we need three angles. These are the Euler angles, right? So basically we know the Euler matrices. So here now we are going to do a different approach. Here we try to get the generators, from the generators get the elements. Here instead of that, we will start with the elements of the group. We know the group elements. These are the Euler matrices that we know from classical mechanics. We know that these are required to describe rotations in a three-dimensional space. And we are going to try to get the generators based on their definition. So remember, the generators are just the, from the Taylor expansion they come, right? So you can see that you get some Jx corresponding to Rx, Jy corresponding to Ry, and Jz corresponding to Rz. And if you again put them back into the sort of exponential expansion, then you will reproduce these three matrices. So you can see that if you take the commutator of any two of them, you get the third one. So this is very similar to what we know for angular momentum algebra, right? So this is basically how angular momentum algebra works, is a similar, very similar thing, but with IE. I think IE doesn't come in. So this tells us that the structure constant is basically the Levi-Civita tensor. So the structure constants being non-zero is consistent with SO3 being a non-abelian group, because in a plane, in a plane, it doesn't matter in what direction I turn. If I do 30, then 40, it's the same as if I do 40, then 30. But if I am in a three-dimensional space, if I first turn in this direction in some angle, then in this direction in some angle, and then the other angle, the order in which I do the Eulerian rotations really matters. They don't commute. So that's why the structure constants are also non-zero. Okay, so you can already see how some physical aspects of the space we are in are immediately mapped onto the they are mapped onto the what is it called, the structure constants, right? Or the structure of the generators and their commutation relations. So you can already see how physics is encoded in the structure constants that we are talking about. So this is the idea. And then finally, let's look at SU2, which is where spinors live. So we approached SO2 by looking at what needed to be preserved, that's the length of the vector. From that, we derived the form of the generator and consequently the form of group elements. We approached SO3 by starting with the group elements, and from that we derived the form of the generators. We'll approach SU2 in another way by starting with the structure constants. So as I said, there are three ways in which we can denote a group. We can denote a group just by its elements, its group elements itself in some particular representation. So remember, when I say group, I mean some particular representation of a group. If you want to show, then either you can show all the elements of the group, that is a trivial thing, or you can show the generators which lead you to that group, and these are particularly for Lie groups. Or the third equivalent way is you can show it in terms of the structure constant. So once you're given a structure constant, how do I then reconstruct the group? So that is what this example is showing you. So you can see that SU2 structure constant ends up being the same as SO3. Okay, and actually it's because SU2 is kind of like rotations in two complex dimension, which is kind of the same as it has some copies. SU2 has copies of SO3 within, or SO3 has copy of SU2 within it. So you can look at the details in this book, but basically SU2 is rotation in two complex dimensions. The most general form is this. Special, whenever you see special, that just means the determinant is 1, and unitary means this. So in other other words, this is the form of a general SU2 matrix. Both A and B are in complex plane and therefore have two real components each. So U has four real parameters. The constraint A square plus B square is equal to 1, which is the unitary matrix condition, fixes one of them, leaving three real parameters just in SO3. This is a loose illustration of why SU2 and SO3 have the same structure constant. They are both rotational groups with three real parameters. But the point is that SU2 will have three generators. Okay, so this is just a kind of a heuristic way of seeing why SO3 and SU2 should have similar behavior. They are both rotation groups. SO3 is in the real plane, SU2 is in the complex plane, but and they have three free parameters as is shown here. Okay, so this is why SU3 is interesting to us is because SU3 describes the strong force and it is a, SU2 describes spinors, and then similarly you can think of SU3, which is the higher dimensional equivalent of it. So you can see that SU3 describes the strong force, and the reason why SU3 is important is because it is a non-abelian theory, and that leads to gluon self interactions which can lead to asymptotic freedom and other things. So again, remember that when I'm talking about groups, ultimately when I'm talking about continuous groups, group theory, all this, I'm talking about symmetry. And why is symmetry important? Symmetry tells us what kind of physical processes are actually happening in my system, right? And then that means that what group I use, what its generators are, and more specifically what its structure constants are, immediately tells me something physical about the interaction or the particles that I'm describing. So this is the idea, this is a funda behind using group theory for the standard model. So you can see that this is, basically from the lecture notes only. You can see that this is basically the sort of generator kind of thing that we're talking about. These are something called gauge transformations. We'll come to that. But you can see how, generators are corresponding to a representation, and there's a fundamental representation as well. So in the case of SU2, you can see what the generators are. They are basically Gelman matrices. So you can see that this is basically shows that the structure constant is the Levi-Civita tensor. And these are basically, there are 8 such Gelman matrices that are possible, right? And based on normalization, you can get it. So yeah, this is some other details, but this is the important thing. Okay, so with all that done, again, if you want more details about this kind of thing, the chapter 3 of this book, Symmetry and the Standard Model, really goes into a lot of detail of group theory, starting from the basics. I really recommend it, so you can look at it. Okay, and of course, all the group theory textbooks I mentioned, but this is, again, specifically to construct the standard model, so it's very relevant for the things we are discussing. Okay, so finally we can talk about the Lorentz group. So remember, now we are talking about Lorentz symmetry or Lorentz invariance, which is a very important ingredient of the standard model. Whatever we write in the standard model has to be consistent with special relativity, which is where this idea of Lorentz group comes in. So you know that there are two kinds of transformations that are possible when we talk about Lorentz transformation. You can have rotations or you can have boosts, right? So rotation is just rotations between frames. Boost is when you increase the velocity between frames. So these are the basic elements of the Lorentz group. You can see that there are 6 matrices, right? And we can, again, you can find the generators of the Lorentz group like this, basically just by doing the same infinitesimal sort of, based on the definition of generator, you can find out what are the generators of the rotation matrices and what are the generators of the boosts. And you can see that you find the commutation. You can, again, this is 4 cross 4 matrices because there are 4 dimensions, right? 3 spatial indices and 1 time temporal index. So altogether, these are 4 by 4 matrices. And you can find the commutation relations between them to find, you can see that rotation seem to be independent, but boosts are kind of like, mixed up with rotation. In specifically, this is because 2 boosts are kind of correspond to a rotation, and this you can think about in terms of what those things actually mean. So it's important to note that, as I mentioned in the beginning, we can take a group and we can then represent it in any vector space we want. right? So I showed you a very simple example from Wikipedia, but this Lorentz group also, as I wrote here, this is the 4 by 4, like, matrices, but you can always write it in any sort of vector space you want. And depending on what vector space you write it in, you end up with, scalar or left-handed while spinner, right-handed while spinner, vector, or this, graviton. So each of these corresponds to a different kind of particle. So zero, this is a spin zero particle, for example. These are spin half particles. This is what you described in the Dirac equation, for example. And then this is, or the photon, for example, is where this is, because a mu is kind of a vector. This is a graviton, which is a theoretical particle theorized to be the quanta of the gravitational field, and it's actually a spin 2 particle. If it exists, people have predicted that it should have spin 2, it should have degrees of freedom corresponding to spin 2. So I'm not going into details because I want to solve the questions. But just go to section 3.3.3 of this book, Symmetry and the Standard Model, same book I've been using throughout. Here you will actually see that each of these scenarios is worked out. Like this kind of mathematics is worked out for each of these scenarios. And from that, you can get an idea of why this is a scalar, why this is a spinner, and so on, why this is a vector, so on. So you can really get an idea of this mathematics more. Okay, so yeah. By the way, SO13 is how it's usually denoted, the Lorentz group. It has two copies of, the while spinners and none. Okay, again, this is important. Okay, so that was like a quick recap of first the Dirac equation and then also a little bit of group theory. So again, it's not very comprehensive because I hope that you've been getting enough things from your lecture notes as well. But again, if you have any doubts, feel free to ask me. And I really recommend, I've put the list of references here. I really recommend this book, Symmetry and the Standard Model for Group Theory, Chapter 3. And generally for QFT basics, I recommend QFT for the gifted amateur. You can, of course, go ahead and read, one of the actual QFT textbooks. But I think for this course level, if you're not looking to do a full semester on QFT, you can try that book because it gives you a lot of intuition. Okay, fine. So maybe we can go to the questions for today. So there are only few of us. So let's try to answer them together, and then we can. Okay, so first question. For rotation generators J and boost generators K, what is the commutator of Ki Kj? So we just spoke about this, right? That the Lorentz group contains both rotation and boosts, and you can find the generators and you can find this commutation relations. Okay, someone says C. Any other answers? Okay, fine, fine. We can just go to the answer. That's fine. If anyone has to leave, that's fine. You can catch up with the video later. But let's just go to the answer. So the answer is actually C. So again, that you can see here that if you work out the generators and then you take the commutation relation, so this is again corresponding to the fact that rotation is kind of independent of boost. We can always do rotations, but if you do two boosts in succession, it's equivalent to a rotation. You can also see that from the metric structure. Okay, so that is why when you take the commutator of the boost generators, it actually ends up with something that involves a rotation generator as well. Okay, next question. Which of the following is not a representation of the Lorentz group? Okay, someone says D. D, okay, great. Correct. So we know again the representation means that I'm mapping it into a particular vector space. So as we saw in the last slide, the tensor representation is like when we have the graviton, for example, the spinor representation is the Weyl spinors, and scalar representation is when we have this scalar fields like we use in the Klein-Gordon equation. Okay, good. So for spinor generators, NLI and LRI, so this I didn't touch on, but okay, I thought I had slides on this. One second. Okay, I guess not. Right. Sorry. Okay, great. Where is it? Okay, so basically, the generators that we saw were in the fundamental representation of the Lorentz group, right? But as you saw, you can also map the Lorentz group onto other vector spaces to get other representations. So the representation in the spinor vector space is what is called the spinor generators. I think you've dealt with this in this. Okay, someone says A. Okay, maybe we can. Since there are only two people, I was just waiting for the other person is answering, or we can go to the answer. Okay. Yeah, correct. So again, the way to you saw exactly what generator means and how you can generate a generator. So again, if you do the representation in the spinor vector space and then you try to reconstruct the generators, then this is what you will get. Okay. Next question. The Lorentz group contains how many generators? Okay, someone says B. Okay, you say C. So go to the answer. The answer is actually B. So we just spoke about this, right? Basically, the Lorentz group has six matrices if you think about it, because there are three rotations and three magnetic fields. Sorry, not magnetic field. I'm so sorry. Three rotation and three boosts that are possible if you write it as SO13, which we just saw. And each of these you correspond to a generator, right? Three matrices. I mean, it's not three matrices. I mean, three types of rotations and three types of boosts. And each of these type of rotation or type of boost can be generated using one of these generators. So we have three rotation generators and three boost generators. So I don't mean that there are only six matrices. Each of these, if you fix theta x to something, theta y to something, you get a whole family of matrices. What I mean is there are three types of rotations and three types of boosts. Okay, so the answer is 6. I hope that's clear. Okay, we can go to the next question. For an abelian gauge theory, the structure constants are. Okay, so A and Give a minute in case the other person is answering. Okay, we can go to the answer. So the answer is zero. So the in an abelian gauge, in an abelian gauge theory or an abelian group theory, the generators commute with each other, and this you can see again in the cases we saw. For example, SO2 is where the generators commuted. Sorry, the matrices commuted with each other, and in those cases, the generators also commuted with each other, and we got a zero as the structure constant. If this is not the case, then the structure constant will be non-zero. Next question. Okay, someone says B. Okay, we can go to the answer. So the answer is B. So we didn't speak about gauge bosons and Goldstone modes and other things today, but basically the number of gauge bosons is equal to the number of generators. This was touched on in the lecture notes, if you remember. Hmm. Okay, I don't have it open here. Let's see. So I hope you have been accessing the lecture materials, but I think in one of them this was mentioned. Let's see. Yeah, so this was about the spinner thing. This we have already covered. So here, for example, you can see that so this is basically about writing the various terms in the Lagrangian. You can write the field strength tensor or the field tensor basically in terms of the structure constants in this way. So for the photon, of course, because it's a commutative theory, the photon belongs to SU2 cross U1. That's why FABC just goes to zero. Whereas for the color or the super the strong force, because it's a non-abelian group theory, a non-abelian gauge theory, this doesn't go to zero. So what I'm trying to say is for the photon, if you remember, the vector potential and field strength are just del mu a nu minus del nu a mu, whereas for the gluon, for example, that is not the case. So the thing that I'm trying to emphasize is that the group theory that we have, the representation that we have, its properties directly map onto physical properties about the objects themselves or the forces themselves. Like a non-abelian group theory immediately tells us what the field strength tensor looks like in the Lagrangian. So this is a gauge transformation, and you can see that the number of gauge bosons is equal to the number of generators, because this is basically a gauge transformation is when we are going from based on some operation, we're going from one to another, and that is leaving the Lagrangian invariant. So that is like how we gauged the Coulomb, like we impose the Coulomb gauge and the Lorentz gauge to make sure that the photon polarizations were reproduced, similar to that. So here you can see that the number of gauge bosons is equal to the number of generators. For SUN, you have n squared minus 1 generators. For example, for SU2, we saw that we have 3 generators, right? 4 minus 1. Similarly, you can see that there are 3 gauge bosons for SU2 electroweak, which is W1, W2, and W3. SU through 3, if you check, there are 3 square minus 1, 8 gluons, and so on. So this is how you think about it, okay? So the number of gauge bosons is just the number of generators. Again, this will be a little more clear when we go into electroweak symmetry breaking and the Higgs mechanism. I think that's how I best understand gauging. But yeah, you can just for now, just know that the number of gauge bosons is equal to the number of generators of the theory. So it is just minus 0. Okay, next question is very interesting. If a gauge boson has self interactions, then A, B, C, or D? Okay, okay, I see an answer. The answer is D. Any other answers? Okay, if not, we can move to the answer. So the answer is actually that the theory may be asymptotically free depending on the number of flavors. This is actually a very, very, very important physical insight, and it won David Gross and Frank Wilczek the Nobel Prize. Maybe someone else was there, but these two people are definitely there. This is David Gross. This is asymptotic freedom. And the interesting thing that asymptotic freedom tells us is that quarks are free at large energies, which is different to, say, the Coulomb force, right? The Coulomb force acts its strongest when particles are close together, but if, say, two electrons are close together, their Coulomb force between them is very strong. But if we try to separate them, then yeah, the Coulomb force drops down, right? As the separation increases, the Coulomb force decreases. Whereas for quarks, because they obey the strong force, they have self interactions because of non-abelian gauge theory. So again, you can see that everything is connected. First of all, quarks belong to a particular group theory, SU3. SU3 is non-abelian, so it can allow self interactions because of the structure constant. And because of all this, what happens is that quarks particularly get the quark force, the force between quarks, which is the strong force, the strong nuclear force, gets stronger the more we separate quarks, right? So that's kind of the reason it was a big puzzle in physics as to why we don't see free quarks, right? We only see quarks, we only can infer the presence of quarks from, say, deep inelastic scattering, that they are present inside protons or inside neutrons. We don't see them as free particles. The reason is because the quark force obeys this kind of thing. What happens is that as I try to separate quarks, the energy, the Coulomb, the strong force actually increases between them to the point where the energy is so much because of the strong force that an extra, it can actually create a quark anti-quark pair, right? And that kind of destroys the hope of making a free quark. So there's always enough energy that we are not able to separate them. Now this works for quarks because they have 3 flavors, but what Wilczek and this guy David Gross showed is that this is flavor dependent. It's like 11f minus, I forget the exact expression, but for a theory to be asymptotically free, basically it has to prefer anti-screening over screening. And this is only possible, which there's a competition between the screening, which is like the antiparticles that surround it, and the anti-screening, which kind of makes the the force stronger. So screening tends to decrease the force. This is what we see in electromagnetism. In QCD, because self interactions, you can have gluons that also surround it, and that kind of makes the force even stronger. So the quark appears even, harder to, go. And the competition between this anti-screening and screening is determined by the number of flavors, number of colors and number of flavors. So yeah, in our world, because we have three colors and three flavors of quarks, it works out that quarks are actually asymptotically free. But in some multiversal theory that you can hook up, where there are actually five flavors of quarks or something, it might not work. I forget the exact details, so I don't know which exactly combination doesn't work, but you can look it up. So there's a very nice account of it in Frank Wilczek's Nobel lecture. So if you just search it up, Frank Wilczek was one of the people who, along with David Gross, showed that this asymptotic freedom is, if you have a non-abelian theory, then asymptotic freedom can be possible in some sort of mathematical formalism. They showed it, and this kind of resolved this long-standing puzzle of why free quarks wasn't there. It's simply because the theory is works in such a way that the more you try to separate the quarks, the higher energy, the more energy you have to put in, to the point where if you want to isolate a quark to infinite distance, which means you're isolating it, you have to put in infinite energy for it to be possible, which is of course not possible. So why non-abelian groups lead to self-interactions is also very interesting, where basically for non-abelian groups, the structure constants are non-zero, as we just saw from our definition of generators and structure constants and so on. So the generators don't commute. So you can see that this way. So if you take a general definition of field strength, it's written as del mu a nu minus del nu a mu minus this is how you construct the field tensor for any theory. And for an abelian gauge theory, the last term vanishes. So for example, for electromagnetism, we know that this vanishes because it's an abelian gauge theory. There's only one a generator. It obviously commutes with itself. The non-abelian gauge theory, what happens is F mu nu, this basically has these kinds of things. And if you put it in, you see that it does not commute. The last term doesn't vanish. So basically, when I write, because in the Lagrangian, I'm going to have F mu nu, F upper indices mu nu, right? So when I multiply these two, I can have something like a mu times a mu a nu, or a mu a mu a mu a mu. Like I can have triple the terms with three a mu's, or I can have terms with four a mu's. So they're basically three vertices and four vertices. These are not present in photon, for example. You can't have a vertex, a Feynman diagram with three photons at a vertex, right? It's forbidden. Whereas gluons can have it, and that's exactly because of this idea, which is that non-abelian groups have non-zero structure constants, leading to non-commuting generators. Okay. So yeah, this is a very nice way in which we can see how the group theory, the mathematical formalism we are using, immediately leads us to resolve physical puzzles. Like people knew that quarks don't exist freely, and it was a big puzzle as to why that was. And to resolve that, it really took group theory and this kind of idea to come in. Okay. So next question. In the adjoint representation, the generators of SU2 are here, someone says C. C. So the answer is actually a set of three 3 by 3 matrices, as you said. So adjoint representation is where we kind of construct the groups using the structure constant itself. And that's kind of what you saw when we did SU2 as well. We saw that the structure constant of SU2 is uh, the Levi-Civita epsilon ijk, and you can see that SU2 has three generators. So basically, adjoint is like the default or fundamental representation, and all the representations will obey this. But if you construct the representation using the structure constant themselves, that is going to be the fundamental representation. So that's going to be a set of three 3 by 3 matrices. In order to get polymetrics and other things, you have to be in some other representation. That's the idea. Okay, good. Next question. In the QED Lagrangian, the value of the electric charge is okay, someone says B. Okay, we can maybe go to the answer. So the answer is any real number in principle. Yeah, in the QED Lagrangian, the charge comes as the fee. Basically, the coupling constant is the theory, and that can be any real number in principle. In practice, it's based on the energy scale at which you have the theory. That number is, and what particles are taking part, and so on. That can be different, right? So it can be any real number in principle. The sort of discretization of charge is not baked into QED. Uh, so it could be, something in principle, it could be anything. But of course, we know that charge comes in discrete packets. Okay. Okay. I think the last question for today. So is this statement true or false? If it's true or false, why? That's the question. Unlike scalar QED and spinor QED, vector QED cannot exist. Is this true or false? Okay, someone says A. Okay, we can maybe go to the answer. So the answer is false. So, there are vector particles which are still charged, right? Yeah, photon, of course, doesn't have any charge. But for example, the W and Z bosons, which are part of the force carriers of the weak force, they are charged. Okay, so they do carry electric charge. So if we are going to write a theory of their interactions, that's going to be a vector QED. So it's going to be the same kind of idea of how to write scalar or spinor QED. It's just that vector QED will involve writing a spin 1 equation and then adding the sort of field strength tensor to that Lagrangian, right? So for a scalar QED, for example, you start with Klein-Gordon and then you introduce the field tensor, field strength tensor to it. For spinor QED, you start with Dirac and then you add the field tensor to that. For vector QED, depending on what the vector is, spin one vector particle like the WZ boson, you start with that and then you add on a field tensor to it. So you can always have electrically charged vectors like W and Z, which require vector QED as well. Okay, so yeah, so that brings me to the end of today's class. I don't think many people attended, but I hope people are watching on YouTube or whatever. Again, I just want to highlight these are the lecture resources that I would use of this QFT for gifted amateur, and this book particularly for this lecture is what I use the most. But these are some other interesting lectures to do with QFT, to do with groups, so that because this course introduces a lot of new ideas for the first time. It might be, and depending on your interest, you want to go deeper into any of these ideas like QFT or group theory or whatever, apart from the resources which are being recommended by the course instructor, I would recommend these as well. These are more of what has helped me in both learning standard model physics and for preparing for this course as a non-particle physicist. These are the things that have helped me the most pedagogically. So yeah, that brings me to the end. So again, I'll just share the links. If you have any topics you want me to cover in the class, please mail me. I am always ready to answer your mails. Sometimes it goes to my spam folder, so if you don't find me replying, just bring it up in the class. So these are live sessions, so it's nice to always have interaction. Otherwise, it's the same as your recorded videos, right? So there should be some difference. So again, I'm just pasting my email ID and the website. You can go to my website and find the links for the YouTube videos, as well as the drive where all the things are there and the links for the YouTube videos. And yeah, if anything else, if there's no other agenda, we can stop for today. So thank you very much for joining. Have a nice week, and I'll see you next week, same time. Okay, thank you so much. Bye.